Am I audible? Yeah. Yeah. First of all, I'd like to thank the organizers for organizing such a nice event. And also I'll talk about this and also giving me the opportunity to present my work here. So I'll talk about this universal subdiffusive behavior at the band edges and the microscopic reason behind this subdiffusive behavior is the transfer matrix exceptional point. And this work has been done in collaboration with Bijay from IISA Pune, Manas from ICTS, and Archak from IIT Hyderabad. So first, the brief discussion about this transport setups and the transport classification I'm going to talk about. So if the central system, this system is attached with two baths with different chemical potential, let's say mu and mu minus delta mu, and the baths have, let's say, identical temperature. Now the particle will flow from higher chemical potential to lower chemical potential. And how the particle will flow through this system, the conductance, conductivity, these are the measure of this thing. So now this is a non-equilibrium scenario. So in the long time, system will reach a non-equilibrium steady state. And in that case, in zero temperature, the fermionic conductance G mu is nothing but is proportional to the transmission probability. What is that? The probability of transmission of particle from this first side to the last side. For 1D system, this conductance goes as, when the conductance goes as 1 by n, so this is the diffusive transport. This is nothing but the Ohm's law. In that case, actually conductivity doesn't depend on the dimension of the system. So it has a well-defined conductivity. So this is the normal behavior. But for the low dimensional system, it happens that often we see departure from this diffusive behavior. We can see different conductance behavior. It can happen G is independent of n. So this is the ballistic transport. Then it can happen G is exponentially decaying the system size. So this is the perfectly insulating state. So there is no transport here. And then G can follow a power law decay like n to the 4 minus delta, where if delta is between 0 to 1, so this is known as a super diffusive transport. And when this delta is greater than 1, so this is the subdiffusive transport. And delta equal to 1, obviously the diffusive limit. This delta greater than 1, this and this this exponentially decaying both shows the insulating in the thermodynamic limit. But for a finite size system, the conductance in the subdiffusive transport is exponentially larger than the perfectly insulating thing. And that's why subdiffusive transport is it's advantageous when we look at the small systems. Now, when do we see this kind of subdiffusive transport? This basically we see in the disordered system. This is generally this is associated with the spatial uncorrelated random or quasi-periodic kind of disorder. And this subdiffusive regime we basically mainly see in the critical regions, which separates localization and delocalization transition. So these are the references of this. So can we see the subdiffusive behavior in the clean system? So, so we have done this work in these two works done by us only. So in the open, if we look at the open clean system, the subdiffusive behavior can arise because of the non-analyticity in the system dispersion. This paper is published in 2021. And here I'll talk about this work. So here we have another microscopic reason behind finding this subdiffusive transport in the clean system. And that is because of this exceptional point of the underlying transfer matrix of the Hermitian system. So in the next slide, let's see what is transfer matrix and what is the exceptional point of the transfer matrix. Okay, so let's say transfer matrix is associated with discrete calculus. So it's always come in when we want to solve this discrete Schrodinger equation. Let's say we want to solve the discrete Schrodinger equation for the nearest neighbor tide warning model, which has on-site potential epsilon and let's say hopping 1. So the discretized version of the Schrodinger equation is nothing but this omega psi I is equal to epsilon psi I plus this hopping terms. This psi I and psi I plus 1, and these are the wave function amplitude of the wave function at ith site. Okay. Now, if we want to write this equation in matrix form, so we can write this in this way: how the wave function at I plus 1 site is connected with I minus 1 site. So this is connected with this transfer matrix. And this, for a nearest neighbor model, this transfer matrix is nothing but a 2 by 2 matrix. Now, if we have a periodic on-site potential with Q periodicity, then this epsilon on-site potential will have repetition after every Q sites. And in that case, we can also write down the unit cell transfer matrix, taking the products of the transfer matrix up to some I equal to 1 to Q. Yeah. Now there's a band structure, it has some connection with this transfer matrix. So let's say we have considered only Q equal to 1. So all the potential are identical and it's 0. Let's say we set it's 0. Then the trace of the transfer matrix will give you the dispersion relation of the lattice. And it's a 2 by 2 matrix. The determinant of this transfer matrix is always 1. And it's easy to write down the eigenvalues of the transfer matrix in terms of the trace of the transfer matrix. Now at the band edges, that is the minimum and maximum value of the dispersion, the square root term vanishes and the two eigenvalues merge, and not only the eigenvalues, the eigenvectors also merge. So at the band edges, we have the exceptional point of the transfer matrix. And so if you have a Q periodicity, so there are Q number of bands, there are 2Q number of band edges, and at all the band edges, we can see the exceptional point of the transfer matrix. So not only that, transfer matrix has this PT symmetry like symmetry, so it commutes with this asymmetry thing. And in that case, that transfer matrix has eigenvalues, only real eigenvalues or in complex conjugate pairs. So when this transfer matrix have real eigenvalue, the symmetry operator and the matrix have simultaneous eigenvectors. So this is the symmetric regime. When it has complex eigenvalue, this is the symmetry broken regime. And there's a transition can happen from symmetric regime to symmetry broken regime via an exceptional point. And in fact, if we change the chemical potential of the bath from system bands to outside bands via the band edges, we can see this transition in the transfer matrix. And how the consequences of this symmetry is seen in the conductance directly. So that I'll show in the next slide how this transfer matrix is connected with the conductance of two terminal conductance. So we can see that when mu is in the system bands, that's the symmetry broken regime. In that case, we'll get ballistic transport. When mu is outside the band, the symmetric regime will get the localized transport. And when mu is exactly at the band edges, so transfer matrix at the exceptional point, and that will lead to a universal subdiffusive transport behavior at the exceptional point. So yeah, so I already previously mentioned that the conductance is actually proportional to the transmission probability of the electron of any particle, and that is nothing but the G mod of G1 in square. And that one can this G1 is nothing but this M mu inverse, where M mu is this matrix. So here Hs is the, as we are talking about the non-interacting system always. So this Hs is the single particle Hamiltonian of the system, and these are the self-energy terms due to the baths. And this, as we are considering the nearest neighbor model, this Hs is a tridiagonal matrix, and this self-energy terms, this appears in the diagonal. So M mu is also a tridiagonal matrix. And this G1 in square, this can be written as 1 by delta n square. So delta n1 is nothing but the determinant of this matrix. Now the determinant, so all the conductance scalings is governed by the determinant of this tridiagonal matrix. And the determinant of this tridiagonal matrix can again calculated using a transfer matrix approach as it is certain. So if you want to calculate this determinant of this matrix, so this is this TQ to the power n, this transfer matrix to the power n will appear here. So this n is nothing but the number of unit cell in your lattice. And at the band edges, this transfer matrix is not diagonalizable. So what you can do a Jordan normal form. You can bring it to a Jordan normal form via similarity transformation, and it will take the form this. And if you want to calculate this TQ to the power n, so as it is in the Jordan normal form, this will give a linear n here. And these are easy to show actually. So, and Yeah. Now this delta 1n is as small n is equal to n by q, this delta 1n is proportional to n, that will give this conductance as n to the power minus 2. So whenever this transform matrix unit cell has the exceptional point, and that is happening at the band edges, one always get this universal subdiffusive scaling of conductance with system size with scaling exponent 2. Yeah. And within the band edge, as the transform matrix eigenvalues are in complex conjugate pair, so this is the symmetry broken regime. So we'll see a oscillatory behavior delta. This determinant will be some oscillatory thing with system size, and the conductance will show n to the power 0. It's ballistic behavior. And the outside the band is this real, this eigenvalues of the transform matrix are the real. So the determinant will be exponentially diverging with system size. This will give a localized behavior. So this is the numerical verification of the result with a binary lattice. Here we have q equal to 2, so we have 4 band edges. So these vertical lines are the band corresponding to those band edges. So here the first plot is the plot of the eigenvalues of the transform matrix. The solid lines are here the real part of the transform matrix, and the dotted lines are the imaginary part of the transform matrix. So here we can see that outside the band edges, these complex parts are 0. So we have the real eigenvalues only. And at the band edges, we have exceptional point. And inside the band edge, we have the eigenvalues as a complex conjugate pair. And as a consequence, if you look at the conductance with chemical potential, we see a non-analytic change at the band edges. So outside the band edges, so it's exponentially decaying. Here is this ballistic behavior, and exactly at the band edges, we have seen the subdiffusive behavior. And in the C, D, and E, we have shown this in different regimes. We have shown this conductance scaling with system size explicitly. So here we have shown the origin of the conductance scaling. The microscopically can come because of the transform matrix eigenvalues. So another important thing about this this result is that this band edge is like a mobility edge like behavior in an open system. So in 1D and 2D with random disorders, so all the single particle states are localized. So this is Anderson localization. But in 3D with random disorder, one can get the single particle mobility edge. And with quasi-periodic kind of disorder, even in 1D, one can get the single particle mobility edge. But here we have shown that without any disorder, one can get the this bandage mobility edge like behavior, this where the bandage can behave as a mobility edge. So, and there's no isolated system analog of this behavior. So not only at the band edges, here in the long range hopping system also we have seen that at the band edges conductance scales as 1 by n square. And for a general 1D finite range hopping model, these band edges are the not only as the number of hoppings are increasing, as the number of neighbors are increasing in this model. So band edges are exceptional hypersurfaces of transform matrix, and that will also lead to a universal subdiffusive behavior. And as these exceptional points are highly sensitive to external perturbation, because of this environmental effect we have shown in this paper, from this subdiffusive behavior, there can be a transition to superballistic scaling of conductance because of the presence of this transform matrix exceptional point. Yeah, so that's it. I'd like to thank my collaborators. And yeah.
Thank you, Madhumita. Any questions? Loga.
Questions. So one is this, when you say there's a band edge,
yeah.
So there are these exceptional modes.
Yeah.
Is the statement that these exceptional modes are carrying the charge? Is that if this 1 by n square? I mean, this was not. So you have a, like a scaling, but and I see that it is related to there being an exceptional mode, but should I just think of this, these particular modes as carrying the charge?
Yeah, you can can think that what is the eigenvalues of transfer matrix. So this is the what is the fate of that plane wave when it moves through that, you change the chemical potential, and what will happen. So I mean, when it inside the band edges, this so you can write the eigenvalues of this transfer matrix e to the power I theta, let's say, when you are inside the band edges, so this theta are real. When you are outside, so theta is some imaginary numbers, but exactly at the exceptional point is some transition is the exceptional point. So it's
Yeah, I think I understand the mathematics of it, but I'm just wondering whether physically I should just, if I just took just that mode,
yeah,
would I see the conduction happening in that mode? That was my question.
yeah. So yeah.
Okay. Okay.
So if for the Fermionic conductance is actually you are sitting at that mode, that yeah.
Yeah.
at the
Okay.
band.
Another question. So as far as I understand, this is like a non-interacting model, right?
Yes,
You know,
it's a
like you have
non-interacting.
a bunch of fermions, you have a band, a single particle band structure
Yes.
which you're filling. Now, you know, like so how robust is these results if you try to include interparticle interactions? Would you still have?
So yeah, that there's I don't know, the mean field level it can happen. So I know the robustness is if you have weak interaction, you have low temperature. In that case, up to some finite size, you can see this subdiffusive behavior. After that, there will be a breakdown depending on the. And with interaction, I don't know, but maybe in the mean field level, it can work.
Okay, because you're saying even the mean field there will be like some average, some kind of a band structure and some transfer matrix and so on. Is that the intuition?
Yeah.
Okay.
Okay, any other questions? Okay, let's thank Madhumita. Thank you.